Let's take a second. I want to run through an example problem really fast. Just a little rushed at the end of lecture today, so let's do a quick example of one of these equilibrium torque situations. Okay, so a question like this could ask something along the lines of what forces are acting at the pivot, right? So if you think about this, I have this rod here, and at the end of the rod, I've tied a basket of cats, 22 kilograms. I don't know how many cats that is. Maybe 22 cats. I don't know. Anyways, so I've got this rod, basket of cats, and then there's another cable here that's kind of tying them, hoisting them up. I don't know, maybe there's like a river down here and keeping them. I don't know. Anyways, basket of cats. So what I want to know is, right, I've got the weight of the cats, I've got the weight of the rod, there's a tension on the cable, right? And so there's going to be some forces here acting at the pivot that's like pushing on this in the X and the Y direction. Okay, so a question like this could say, hey, like what forces are acting at the pivot? So to work on a problem like this, the first thing you're going to want to do is along the rod, you're going to want to draw, well, what are all the forces that are acting on this thing? Okay, so first thing you do is, oh, I've got forces just coming in. You want to put the center of mass, right? The rod is going to have a weight, and so the force of gravity is going to act on the rod at the center of mass. So that's the first one I'm going to put on there. Okay, so there's that. And then, so this is just like drawing a force diagram, except for it's not a free body diagram. It's going to be a force diagram of all the forces acting on the rod, where they act on the rod. Okay, so once you put the weight on there, then you say, well, what's touching the rod? Well, the pivot is touching the rod. Okay, and at the pivot, I'm going to have a force. There's going to be a horizontal force, a force in the X direction, and a force in the right direction, and a force in the Y direction. I don't know what the values of those forces are, but I do know that they have to exist, right? So I've got the forces at the pivot, okay? Then what else is touching the rod? This cable is. So there's going to be a tension force acting in this direction, acting on the rod. And then I've got this tension force here, right? It's the weight of the kittens pulling down at the top of the rod, okay? And there's nothing else touching the rod, so we're done, right? I've put all the forces on here. Okay, so where do we go from here? Well, so the next thing you want to do is choose a place for this to act. Actually, we'll look at that in a second. With all of these problems, you're going to take two approaches, okay? The first thing we want to do is just balance the forces like we normally do. Like we see this rod, we know it's not accelerating horizontally, it's not accelerating vertically, right? So that means that the horizontal and vertical forces must be in balance, okay? So starting with the vertical forces, if I look, I've put all the vertical forces in yellow. There's only one vertical force on here that's up. So the Y part of this, of the pivot force, must be equal to the weight of the bar and the weight of the kittens. Okay, so the Y part of the pivot force is equal to the weight of the bar plus the weight of the kittens. Okay, now, well, I know how much the bar and the kittens weigh, right? So 15 kilograms, 22 kilograms, so that's 150 newtons, 220 newtons. So the Y part of the pivot force, I'm already halfway there, right? What forces act at the pivot? I'm already halfway there. 370 newtons of vertical force acting upwards at the pivot. Great. So what about the X part? Okay. Well, this X part of the pivot, well, that has to be equal to the tension in this cable. Okay, you know, this comes here at a 90 degrees. That must be equal to the tension there at the cable. Okay, it'd be really mean to move this cable up here, because I could have had this cable come down at an angle. Then the cable would have both a vertical and a Y component. But right now, the way that it's attached, there's only a horizontal component. So the X force at the pivot has to be equal to the tension. And if this was all we had, I'd be stuck. I couldn't figure the rest of this out. But luckily, that's not all we have, right? The next thing we're going to do is we're going to balance the torques, okay? Because this rod could be rotating, okay? And then, now at this point in the problem, okay, what you want to do is you need to put the pivot somewhere, okay? Put that pivot place where all the torques are going to act around. Now, the natural place to stick it is right here, where the actual pivot is, and then and because the cool thing is that you know that torque is force, the force acting times the length of the lever arm, right? How far is that force away from the pivot? And then the sine of the angle between them, right? Like we talked about in class. And if I put the pivot, the pivot place right here at the pivot, then these two forces, the distance between them and the lever arm is, and the pivot is zero, right? So these, with the pivot here, there's no torques. Now, because we know the system is not going to rotate, I can actually put the pivot wherever I want. Now, if the system were to be in rotation, then I'd have to put the pivot here. But I could put the pivot here and cancel the weight of the rod, and then I'd have to use both of these and these two to balance the torques. Or I could put the pivot here, or I could put the pivot here. Really, you want to put the pivot somewhere where it's going to eliminate the most number of variables. And this will make more sense in some of the other problems you look at, and we'll do some more examples in class. But for right now, we're just going to put it here, okay? And okay, so with the pivot there, now balance the torques, okay? So I don't need to worry about either of these forces; those torques are taken care of, okay? But I can come over here. Right now, I need to look at the torque from this force, right? And that's what this is coming. So here's the force, the weight of the bar, times the distance, right? So this distance from the pivot out to where that force is acting, that distance. So that's half the length of the rod, okay? Because it's acting at its center of mass. Excuse me. And then I need the sine of the angle between them. So that's going to be this angle right here. So if this angle is 30, then this angle that's going to complete it, the 90 degrees is going to be 60. Okay, so I've got the force times the length of the lever times the sine of the angle between them. Okay, plus now I got to do the weight of the cats times the length of the lever arm. So that's going to be 3.2 meters in this case, the full length of the bar. Times the sine of the angle between them, and that's going to be 60 degrees again, right? Those are the same angles. Okay. Then these two torques are trying to turn this bar clockwise, but this torque is turning it the other way. So that has to. So this the torque from the tension is going to be equal to these two torques combined, and so I'm going to have the tension force T times this radius, so the length of the lever from here to where the rope is tied, the radius at the tension, times the angle between them, and that's 30 degrees, okay? So I have this equation here, and I'm just going to fill in the numbers that I know. Oh, by the way, this length is I've got this little triangle here, right? And so this opposite side is 1.5 meters up. I've tied this cable. So the sine, because that's the opposite side, this SOHCAHTOA, the sine of 30 degrees is going to be the opposite over the hypotenuse, and the hypotenuse in this case happens to be this radius at the tension, or the length of that lever arm. Okay, so excuse me, that ends up being 3 meters. Okay, so I've got this thing going on here, and 150 is the weight of the bar at 1.6 meters, sinus 60. 220 is the weight of the cat. Full length of the bar, 3.2 meters, sinus 60. The tension acting at 3 meters, sinus 30. And I know everything but T, so I can solve for T. So the tension is 545 newtons. Okay, so now I can make this little triangle of the forces at the pivot. I've got 545 newtons here and 370 newtons vertically, right? Horizontal and vertical. And then I can find the resultant force. So use the Pythagorean theorem. So there's 685 newtons of force acting at the pivot at an angle of 34.1 degrees. Okay, so that is the force at the pivot. And these are the components of that force. So there's a lot going on here, but all of these problems are going to follow the same pattern. Draw the forces acting on the bar, balance the vertical forces, balance the horizontal forces, and then balance the torques. Okay, you're going to do, it's that same process over and over again every single time. We'll do some more examples. I hope this helps, and I'll see you all on Thursday.